Okay, cool. It's live.
Okay, so do you want me to start with conceptual
Yeah.
stuff with recursion?
Yeah.
Hi, Dana. So today's webinar is going to be on recursion. So before we get started, have you gone into recursion at all in your classes? Have you at least heard of recursion?
Oh yeah, I have some experience with recursion and things like that.
Oh, okay.
Good.
So then you should find this pretty straightforward then. Okay, so first starting out with conceptual nature of recursion. So recursion is basically when a method calls itself. So like if you know object-oriented programming or Java specifically, you have methods, and methods can call other methods, which can call other methods. Recursion is basically the unique case where a method will call itself within the method. So let me actually share my screen. Okay, wait. So can you see my screen?
Mm-hmm.
Okay, so if I made, let's say, public int a method called recursion, I pass in an n, and saying like return recursion of n. That would basically be a recursive method because I'm calling the method name, which is recursion, within the block of the method. So when you do return recursion, it's basically just going to just call the method again, and then it's going to call the method again, and then call the method again, because you're keeping a method called to recursion and passing in the integer n. So you can basically think of it as kind of being like you have like a mirror, and like it reflects a picture, and then the picture gets smaller and smaller and smaller. That's kind of like what recursion is. You keep calling the method over and over again. And one of the things why we use recursion is because it's elegant. So with one construct that we know to like loop through items is loops. So like if you want to, let's say, like sum all the digits in a number, then you could use a loop to do that, but you could also do it recursively, and that's one of the examples that we're going to go over later. And the code just looks, I don't know. Some people think that the code just looks better because it's easier to read, conforms more to the mathematical representation of like what the code would be. So first, I'm going to talk about recursions and when you would stop a recursion. So in recursive methods, the time if you just call the method and then pass in the same parameter, you would get what's called an infinite recursion. So like, let's say that, let me make this static. I call recursion and I pass in 4. Wait for this to process. Wait, hold up. Assertion failure. What? Turn recursion n. I don't know if it's failing before we can even. Okay, there we go. So if I go into this method called recursion, then basically what it's going to do is it's going to return recursion of n, and n is 4. So it's just going to call this method again, recursion, n is still equal to 4. is going to return recursion again, and again, and again, because this parameter of n hasn't changed. So if you keep going, I mean, eventually this is probably going to like blow the stack, and it's going to be called an infinite recursion because it never stops. So having recursion is we need a base case or a stopping case. Basically going to say, okay, if you reach this certain point, then we want like a specific value. So one thing, the example that I use for, or that my teacher used for recursion is called the Fibonacci sequence. Dina, have you ever heard of the Fibonacci sequence?
Yeah.
Okay. Have you done the code for the Fibonacci sequence with recursion?
Mm-hmm.
Oh, okay. So this is going to be pretty easy for you, I guess. So like, you know, with a Fibonacci sequence, you have the first two numbers, and then you add those two numbers to get the third number, and then you add the second and third number to get the fourth number, and so on. So with this case, you need a base case to what your first two numbers would be. So like, there are different ways to like think of it, but like a lot of people say like the first number is 0. And people say that the first number is 1. It really doesn't matter in the end. I'm just going to say if n is equal to 0, then return 0. If n is equal to 1, return 1. And then our actual recursive call will be return Fibonacci n minus 1 plus Fibonacci of n minus 2. And basically this recursive call will return the n minus 1th term of the Fibonacci sequence and the n minus 2th term of the Fibonacci sequence, assuming that n is greater than or equal to 2. So if we run this, let's say we want to find the 5th term of the Fibonacci sequence, and we'll store that in 5th term. So right now, n is equal to 5. Trying n is equal to 1. And so now, since n is equal to 1, we're going to return 1. And then we go back. We throw that frame off the stack. And that's kind of what recursion is built off of, is stack frames. So you can visualize like the stack frames here. And now that we're in the Fibonacci method, it'll basically, every time that the Fibonacci method is called, it's going to throw another method onto the stack. And once we get to the base case, turn, and it'll throw that frame off the stack. And then go back into the last stack that was called. So like in this case, the last stack that was called, n was equal to 2. We call that again, and then n is now equal to 0. And then we return 0. And so now we have a return value. And we throw that off the stack, go back to the last stack we were at, where n is 2. And just keep doing that. Throw it off the stack. Find that n is equal to 1. Return that. Return value is 2. Throw that off the stack. And so on. Basically, the 5th term we have was 5. We're actually, yeah. This returned void, so we weren't able to see what the 5th term was. But yeah, that's basically how you would do the Fibonacci sequence version. And that's, think of for that. The syntax as you can probably see, is that you just you use the method name, and then you use the same parameters that you would for the method, and make sure that they have the same type. So in this case, n-1 is an integer, so you want it to correspond to n, which is also an integer. With base cases, with recursion, you can have like anything really you want, like before, I guess, the recursive step. So if you wanted, you could have a loop, but usually we just have if-else statements to represent our base cases. Because whenever we call the method and we're checking what n is equal to, then we want to stop at a certain case. So like if n is equal to 0 or n is equal to 1. So yeah, that's pretty much the syntax and general concept of recursion. Are there any questions?
And no.
Okay, so I guess we can go to, should I go through the factorial example or the sum digits example?
Have you seen the factorial example, Naraz?
I haven't seen the factorial example, no.
Okay, maybe we should do
Okay.
that one then.
Okay, so have you learned about factorials in your math classes?
Yeah.
Okay,
Like I understand
so
how it's like multiplying each.
okay, so like if I were to say what would be 4 factorial, like how would you calculate that?
Like it would be like 4 times 3 times 2 times 1. You'd just be like multiplying the previous number, like the numbers preceding it. So that'd be 24.
Yep, exactly. So a general way to, I guess, to emphasize this or to represent it with recursion formula. So like for the general formula for a factorial is that for any n is greater than 1, greater than or equal to 1, you have n factorial being n times n minus 1 factorial, and n minus 1 factorial is just n minus 1 times n minus 2 factorial, and then so on and so forth. So our recursive step would be return factorial, or sorry, return n times factorial of n minus 1. So this would basically give you the factorial of n, because you're multiplying n times n minus 1 factorial. And n factorial is just n times n minus 1 factorial, or n times n minus 1 times n minus 2 times n minus 3, and so on and so forth. Now, what would be the base case in this situation?
So I guess if like the base case is like if n equals like 1,
Okay, so if n equals 1, then what would happen?
then just return 1.
Yep. You also could do if n equals 0, because 0 factorial is actually just 1. I mean, why that is just it's a fact.
Yeah, I think it's like definition or something.
Yes, it's just a definition. So
The only good explanation conceptually that I've heard for why 0 factorial is 1 is that you're taking nothing, and their factorial is used a lot for permutations. And so like there's only one way that you can have a combination or permutation of nothing, and that's nothing, which is 1. So that's the only explanation that I've ever heard for the conceptual nature. But even then, that one is messy.
So I guess it's like permutations and combinations are like for different choices. Then if you have one choice, it's basically the same as having no choices at all.
Essentially, yeah.
Okay.
Because there's only one way you can order it, and it's either that one thing, or it's the fact that you have nothing. So yeah, they're essentially equivalent.
Okay. Thank you.
Yeah, so if we're to step through this code, I mean, you already know what the answer is, but just wanting to visualize it. Um, so you can see that we're stepping through it. If n is equal to 1, it's not going to the recursive step, and now we're calling factorial of n minus 1, and n minus 1 is equal to 3. Return this times factorial of n minus 1. Then n is equal to 2 now. And now n is equal to 1. So, and this is our base case, so we now just return 1. And we throw that off the stack, and now that value of 1 is going to be stored here, and just multiply, then throw that off the stack, and 2 is now going to be our value of factorial n minus 1. And so we multiply 3 times 2, return value is going to be 6. Then we throw that out the stack, and then we finally have 6. And in the first frame, n was equal to 4. So now we have 4 times 6. So that returns 24. And now 4 factorial is 24. And that is our return value. So does that make sense?
Yeah, that makes sense.
Okay. Is there anything else that you wanted me to go over, Asa?
I think something that I've been wanting to work on is like if you have a recursive program, like counting like how many times like it's like called.
Mm-hmm.
Oh, okay. So that like tracing through recursive code.
Yeah.
Okay. Well, I have to actually go soon, so unfortunately won't be able to help you with that, but Asa will be here.
Yeah.
To assist you with that.
Okay.
Okay. So, see you later, Steven.
I can stop sharing my screen then.
Yeah, so I can help you with that one. So was that do you have a specific problem in mind? Like, was it in a worksheet or
I'm not saying that
in general?
I guess just in general, I guess.
Okay. So we can adapt this problem that we made, I suppose, so that we can answer like what the how many times it's going to be called, as well as like what the actual return value is.
Mm-hmm.
So here we go. I'm going to send the link to you right now through the Google chat.
A second, what? What? Wait, so he regraded. Okay, never mind.
Oh, hey, Steven.
Oh, hey. Sorry, I was looking at something.
It's all good. No worries. So yeah, do you see the example, Dana?
Mm-hmm. Yeah.
Okay, so I guess instead of, well, in addition to trying to figure out like what is actually returned, we can also trace while we're doing so how many times it's going to be returned. Because unfortunately, there's no really easy way, like, or easy formula of doing it. You kind of just need to trace it out and get it done.
Okay.
So, time to take out our handy dandy pieces of paper
Mm-hmm.
and get the show on the road. Okay, so do you have any special way, or has your teacher showed you any techniques when it comes to tracing recursion on paper?
I don't think it was like any dedicated like technique.
Mm-hmm.
Just like kind of just going through. So I guess yeah.
Is it did you find that like confusing? Would you want more like clarification with that, or you think you're solid on how to do it?
I think like I was a bit confused on how to like do this though.
Okay, perfect. Yeah, that I know for me personally, it was something that I struggled with because it's really hard to visualize the fact that like essentially like 9 method calls are running at the same time.
Mhm.
But I found that this method worked. So uh, let's for an
Also, I have to
example.
go. Just FYI. So, all right. So, see you, Dana. See you, Asta.
Okay, see ya. Have
Yeah.
fun. Okay, so let's go back to the example that Stephen did with factorial.
Mhm.
So say we're trying to call factorial 4. So first thing you do is I tend to do like, just for ease of mind, I tend to do like a simplification of what the formula is, or like the method names, sorry. So
Mhm.
instead of factorial, I'll just write f. And then this is our first call, right?
Mhm.
So we know that factorial ends up returning 3 times, and then it calls factorial again, but of 3. So what I actually do is I draw an arrow from the original method call straight down, and then it shows like what is being returned. So
Oh,
in the case of factorial, it'd be 3 times another method, and then I keep on doing that process. So under f of 3, I return oh wait, no, this should be 4 times, sorry. I was like, this is weird. Let me where's my eraser? Here it is. So 3 times f of 2. This is what it should be. Sorry about that.
okay.
So it's returning, the factorial itself is going to be f of 4 is returning 4 times 3 factorial, essentially.
Mhm.
And then 3 factorial is returning 3 times 2 factorial. And then we keep on doing that. 2 times 1 factorial. And then 1 times 0 factorial. And we know from our base case that 0 factorial is 1.
Mhm.
So we know that the number it's returning is going to be 1. So as soon as you hit like a number, basically, so once you hit the base case, you're like, okay, sweet, I can do this now. So we know that it's all multiplication, and we know that f of 0 is equal to 1. So that basically evaluates to 1 times 1, which is 1. So I kind of draw an arrow to the side to know that this row evaluates to 1. So we know now that f of 1 is 1. So now we can do 2 times 1, which is 2. And we know now that f of 2 evaluates to 2. So 3 times 2 is 6. So we know now that f of 3 evaluates to 6. Yeah, that's 6. Uh-huh. It evaluates to 6. And so we know that 4 times 6 is 24. And so now we know that f of 4 evaluates to 24. And then that's what ends up getting returned. Does that make sense? Like how I wrote it out?
Yeah, I haven't like. It's nice how it's like organized like that. You can like see each of the calls.
Yeah, that's the recursion is pretty easy to understand. Like because just a method calling another method, or calling itself rather, over and over again. But the hardest part exactly comes with how you write it. Because there are some ways that make it very difficult to see how the compiler is essentially executing the calls. But if you write it neatly and line by line, taking up as much paper as you need, it makes it a lot easier. Yeah.
Yeah.
So you're sure it makes sense, right?
Mhm.
Before we start on the example problem that I sent in the link. So I guess, do you want to try it out on your own first, or do you want to work through it together?
I'll try it out.
Okay, solid. So yeah, let's count not only what the return value is going to be, but also how many times the method is called. Okay, so let me know whenever you're done.
All right. So I got that this was it would return a 24.
Mm-hmm.
That there are, let's see, 1, 2, 3, 4, 5 calls.
Mm-hmm. Okay, walk me through how you did it.
Okay, so I have like f of 5 and 9. So
Mhm.
since that doesn't fill the base case, it'd be like 9 minus 5, which is 4, times f of times f of 5 and 8,
Mm-hmm.
and then so that would be the second call, and
Mm-hmm.
then that would return 8 minus 5 times f of 5 and 7, which is the third call,
Mm-hmm.
and then f of 7, uh, uh, f of 5 and 7, it would return 7 minus 5 times f of 5 and 6,
Mm-hmm.
which is the fourth call, and then that would return 6 minus 5 times f of 5 and 5. And
Mm-hmm.
so uh, since um, since b in this case is like equal to a, it would
Mm-hmm.
return 1.
Mm-hmm.
So that would be 1 times 1, which is 1.
Mm-hmm.
And then like f of 5 and 7 would be 2 times 1, which is 2. And then f of 5 and 8 would be 3 times 2, which is 6. And 5 and like and then f of 5 and 9 would be 4 times 6, which is 24.
Yep, you got it completely on the dot. Yep, that's exactly how you do it.
Okay.
Have you heard of last in, first out? I don't know if
Hmm?
they still teach that in AP.
I have not.
Okay, so this might be going a little bit out of scope, but I think it's really important to understand. So, the way methods are executed by the Java like machine itself is under a process called last in, first out. So the idea is that um, each time you make a call, at least for recursion, right? Each time you make a call and it's not completed, you place it on the stack. So I don't know if that's visible, but basically the first time we called the method, foo, I believe, it was for 5 and 9, right?
Hmm.
And since that wasn't finished, it doesn't come off the stack because it's still being executed and run. But now the next method call goes on top of that. So that's like 5, 8. And this process keeps on continuing. So then 5, 8 is never truly finished because we need to execute 5, 7. So that goes on top. And then we need to uh, execute 5, 6 because that's also part of the whole return statement up until you hit 5, 5. And since 5, 5 um, is like the end of the stack because afterwards you hit the base case. So then since you're now at like the end, what you do is you execute backwards. So just like anytime you have like a stack of plates is usually the analogy. You start off with like the first plate, and then you put the second plate on top, and then you put the third plate on top, and then the fourth plate and the fifth plate. And when you want to take a plate, you start with the one on top. So that's the same idea here with last in, first out. So technically 5, 5 was the last method to be put into the stack, but that's going to be the first one we execute. And just like we did when we were tracing it out here, this was the first one that we executed. And then we did this one, and then this one, and this one. So it's just like in our little stack drawing that we first finished off by 5 because it hit the base case and it satisfied it, then we were able to execute this one, and then this one, and then this one, and then this one. Does that make sense?
Yeah, that makes some sense. Yeah.
So that's just like how the Java machine itself executes recursion, because it just basically makes a stack of all these method calls, and then once you hit the base case, then it's like, okay, yay, we have a final like consolidated answer. Like we know exactly what this method call equals, and then we basically pop like all the different method calls off the stack and execute those. So it's just another way, I guess, of visualizing it.
Okay, so is this for like general recursion, or just for Java, or like the last in first out idea?
Hmm. I know for certain it's for Java. I don't think other languages do recursion differently, just because it wouldn't really make sense otherwise.
Yeah, I don't think it would make sense to do it in a different way, I guess.
Hmm. Yeah, but it's not something I'm terribly sure of, so don't take my word for it. But
Okay.
I think I'm pretty sure, at least for like the AP exam and stuff, it'll definitely be last in, first out.
Hmm.
LIFO. So, do you want to do some more example problems?
Sure.
Because you have a really good grasp on recursion. So let's actually go to the ebook and look at the hard questions.
Okay.
We're gonna have some fun in here. So I can send you the link. Doo-doo-doo. Okay. So let's look at the first question.
All right.
So the following method will return true if and only if ... So let's see. Oh, do you want to try it first before we go over it?
Okay, so I think the answer for this would be C.
What's your thinking?
Well, I had a few test cases, but it'd have to be like next to like it seems that the base case is that like either the string is of less than 2 characters long, or that which would automatically make this return false, or like the first and second character are equal. But like if there's like any two like there could be 2 characters that are equal, but somewhere in the middle of the string. But and to find that, it takes off the first letter of like the first character, and then calls this method again.
Yeah, you are correct. C is the answer.
Okay.
Yeah, I have to admit, like, I actually got that one wrong when I was doing it at first, because I fell into the trap of, oh, like, it'll evaluate for lazy evaluation, so we don't need to worry about the second part of the OR. And so I thought, like, because of that, it would you only need to check the first and the second one, but that's actually, well, that's not right. Because exactly like you were saying, that it'll still keep on chopping if the first one evaluates to, if like the s dot caret equals s dot caret 1, if that evaluates to false, it'll still check the second statement of the OR to make it true. And so it'll keep on evaluating. So clever.
Wait, you said something about lazy evaluation? Like, is that just like if the first case, like if s dot caret 0 equals s dot caret 1, if that was true and it just didn't check the second case, would that be an example of like lazy evaluation? Okay.
It basically, I know it's also called short circuit evaluation. I don't know if you've heard of that.
Oh yeah, that sounds more familiar.
Okay. So yeah, it's exactly like you were saying. Because for a truth statement, that you only need one of the sides to be true for the whole statement to evaluate to be true. So if you know that the first portion is true, the Java itself won't even check the second half, because already the first half is true, so the whole statement has to be true no matter what. And it actually works the same way with and statements, but for false. Because for something and something, if the first thing is false, the whole thing will evaluate to false. So yeah, that's how it works.
Okay, I think that like my teacher mentioned short circuit evaluation for uses of and, if there is a possibility of like dividing by 0, like first you check if like n equals 0, like n equals 0, and then you want to like or like 3 divided by n is this. You want to check if n is 0 first, and if it's automatically false, then it will evaluate the second part.
Yeah, exactly.
Okay.
That's exactly it. Because Java is very lazy, just like us computer scientists. So if it can do the work in as short of a way as possible, it will. And so for and statements, that the only way that it's true is if both sides are true. So if one side is false, then automatically the whole statement is false, which is how it does the division by 0 thing, and avoids having that by having the and statement and checking that it's 0 first.
Okay.
Yep. Does that make sense? Yeah, it's something that the AP exam is often very sneaky. Like some questions you think are right, but then it turns out, oh wait, it was lazy evaluation. That's the reason why it doesn't work, or something like that. So it's one of those things they never explicitly test, but they put it in a lot of other questions as like part of it. And so it becomes very, very lazy and very messy because of that.
I mean, it's what they have.
So let's look at
it's like a good skill to have.
Yeah. It's like it's testing you on your like fine detail knowledge, which is really good. because that shows you have a really strong understanding of computer science.
Mhm.
So it's just like one of those things you have to keep in mind that lazy evaluation is a thing.
Mhm.
Yep. Okay, so let's look at the second question. I think we'll have time for maybe like one or two more questions.
Okay.
So given the following method declaration, what will redo 82.3 return? And let's also add another statement for, let's see how many method calls there are.
Okay. So I think redo 82.3 would return 5.
Mhm.
And that there's 6 calls.
Yep, that's what I got. So explain your methodology.
So I have like redo 82.3, which would be like redo like 82 divided by 3, and since they're both integers, it would be just 27.
Yep. That's like the trick, the little twist that they have on it. Good thing you caught it.
So it'd be redo 27 3 plus 1, and redo 27 3 is just redo 9 3
Mhm.
plus 1, and then redo 9 3 would be redo 3 3
Mhm.
plus 1, and then redo 3 3 would be redo 1 3 plus 1,
Mhm.
and redo 1 3 because like since again they're both integers,
Mhm.
1 divided by 3 would just be 0.
Mhm.
And so the base
Yep.
case, if I is 0, then just return 0.
Mhm.
And so 1 3 is just like 0 plus 1, which would be 1.
Mhm. Mhm.
And then you would have like 1 plus 1 equals 2, and
Mhm.
2 plus 1 equals 3, 3 plus 1 equals 4, 4 plus 1 equals 5.
Yep, you got it. It seems like you have a really good grasp of this, like especially conceptually, which is really, really important.
Okay, but
Is it something that you spent a lot of time on in class?
um not quite, but I think it's because like now I'm taking like specific time to do each of these, but like a skill that I need to learn is like being able to like pace myself on the
Mm. Mm-hmm.
And I've seen a few questions where they're like a multiple recursive calls, like it calls the recursion like twice. Like for example, for this problem, it could be else return redo I divided by j plus 1
Mm-hmm.
plus redo I plus 1 or something like that.
Oh yeah, multiple recursions do get pretty messy. Yeah, but if you understood the Fibonacci sequence, and like when you did it in class, then you'll definitely be able to get it, because I don't think they ever go more than 2 recursive calls.
Okay.
Yeah. Because yeah, essentially, just doing like, I guess some quick, just how would you, whoops, like how you would trace it. So say we have, like, yeah, let's say we have some recursive method called f, and if f is equal to 0, then it's going to return 0, else it's going to return f of, n minus 1 plus f of n minus 2. Sorry, I'm just like really messily writing this. But the general idea is that you're going to call some method called f. It's going to take in a parameter. If that parameter is 0, then it's going to return 0. Otherwise, it's going to call the method again with 1 slightly less or 2 slightly less. And so the way you want to approach this is to draw a tree instead of doing the whole arrow thing, because then it starts getting messy with just in general. So say we call f of 4. So that would be like the top part of your tree. And so we know that f of 4 is not equal to 0. So we're going to return f of 3 plus f of 2. So we actually draw like 2 branches coming off of the tree. And then I just join them with a plus sign, just so I can remember that the operation connecting them is addition. And then now we have 2 different methods that we need to finish executing. We need to do 3 and then 2. In this case, it doesn't really matter the order in which you do it. I tend to try to finish all of them up for 3 first, and then I go back up and finish all of them for 2. So for this case, we know that 3 is not equal to 0. And so because of that, it would be f of 2 plus f of 1. And so now we keep on executing. So for f of 2, it'd be f of 1 plus f of 0. And then for f of 1, it is f of, let's make this if f is less than or equal to 0, so that we don't need to worry about negatives and infinite recursion. So then for f of 1, it would execute to f of 0 and f of negative 1. So usually you would start popping up the stack now because you hit a base case. But since we have a lot of still undone method calls in the tree, I find it easier just to keep on tracing for all of them until we hit all the base cases, and then we start like popping up off the stack. So I will go back up here to f of 1 and start evaluating that. So that would be f of 0 plus f of negative 1. And then back up here, we have f of 2. So we would evaluate that to f of 1 plus f of 0. And then f of 1 would be evaluated to f of 0 plus f of negative 1. So the tree starts getting a little bit hectic. But you still get the idea that each method is having its own like sets of recursions. And so because of that, we need to like trace it all down to each individual base case. And so we said initially that we want to return 0. if it's any time less than 0. So since this is f of 0, it satisfies the base case, so we know this is 0. We know that -1 is also less than 0, so it's also going to return 0. So you have 0 plus 0. So I tend to just note that down. So now it's very similar, essentially, because we're just going back up the stack. So we know that this value evaluates to 0 plus 0. So now we know that f of 2 evaluates to 0. So I would just like note that down somewhere. We know that -1, 0, these two are 0, this evaluates to 0, which means that f of 3 evaluates to 0. And basically you just keep on going in this pattern. It's still very similar to what we did in the past. Does that make sense?
Yeah, that makes sense.
It's essentially what we did with single recursion, but it's just going in multiple directions. So sometimes that gets confusing, but since you really seem to have a good grasp on the idea of like how things, like the function returns this, so that has to get plugged in +1, then it returns that. Once you understand that, then it makes multiple recursions a lot easier. It's just about keeping everything neat and keep making sure you're not flustered or anything.
Okay. So for this function, they just have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 calls.
Let's see. 1, 2, 3, 4, 5, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yep, 15 calls. Yeah, multiple recursions get really, really messy.
Mm-hmm. Yeah, this tree is
and then
like.
it gets really taxing on the system.
Mm.
What were you saying? Sorry, I interrupted.
No, it's fine. I was just like when we were going over recursion in class, we usually focus more on like the end, like result, like what the method finally returns. But
Mm-hmm.
like I get questions saying, "Oh, how many like calls that there are?"
Mm-hmm.
So,
Yeah. Yeah. Sorry.
no, I didn't.
Okay. Yeah. I mean, I don't think there really is any way of figuring out the number of return calls, um, other than doing it. To
All
be
right.
honest, like, because I suppose you could. No, I think honestly your easiest bet would be just tracing it out, because then you know for sure how many there are, as opposed to relying on some formula which may or may not work depending on the conditions. You know what I mean?
Mm-hmm.
Yeah.
Okay, this
And
was
also,
helpful.
I'm glad. Yeah. You have a really good grasp on recursion, and that's one of the tougher topics, so that's going to really help you. That's really, really impressive. I know that was one of my worst topics, I think, when I took the AP exam. Yeah.
But it's nice that I still have like this practice of like tracing through.
hmm Yep, it's all just about practice, to be honest, and like making sure you start early enough so you get as much practice as you need.
Mm-hmm.
Yep. Are you guys, have you started basically doing AP review in your
Yeah.
classes? Oh, solid. Okay. Oh, are you going to be coming out to our in-person session, either online or in person?
The in-person session that's next week, right? Or is
Mm-hmm.
that? Yeah. Okay. Yeah, I think I'll be able to go.
Yay! Oh my gosh, I can't wait to meet you then. And then we're definitely just going to be doing AP reviews. So, if you have any topics that you want to go over, feel free to shoot us an email, and we'll make sure to get questions that are about it.
Okay. Thank you.
Welcome. Do you have any other questions?
Not right now.
Okay. If you do have any other questions, feel free to shoot us an email or sign up for a one-on-one tutoring. Sorry. I guess other than that, I guess we'll call it a day. So see you later. Have a good weekend, Naraz. I mean, sorry, Dana. I just read your thing.
No, it's fine. It's fine. Okay. Yeah. Have a nice day.
Bye.
Bye.